see. Cool. Okay. Okay, good. My name is Syed. I'm a network engineer at Oracle Cloud Infrastructure. And I want to thank you, Oracle and Tesudo, for sponsoring the hackathon. I want to thank you, NANOG, for organizing the hackathon. I want to thank you, my teammates and colleagues who helped me actually throughout the building up the hackathon and then on the Sunday running the hackathon. So just a quick recap. It was the 8th hackathon organized by NANOG. We roughly had 50 participants working in 10 different teams. There were a lot of college students, so it's always great that there's a chance for college students to come and work with network professionals. We had a bunch of first-timers, so that shows there's always room to grow and new people to show up in the hackathon. Hackathon goals. So the theme of hackathon was deploying active monitoring infrastructure. Each team has a task to extract the topology using some kind of automation from a network. Use that topology information to build a network map or network graph. And once they had a network map, they had to calculate all the possible best paths between any two given endpoints. And once they had all the best paths, they had to make sure they can probe all those best paths and record any failure as it happens on any of those paths. So how the experience of the day was. So we started the day with giving an overview of hack and what's the topology information look like. We gave them an overview of different tools they can use to solve the problem. So it was interesting throughout the process that how many people actually know about ExaBGP but never had a chance to actually work on ExaBGP. So it was a good chance for them to get some hands-on experience with ExaBGP. There were some participants who never heard about BGP, address family LS, or worked on a tool called Scapy in Python. So it was a good experience, learning experience for them as well. So the team started working on hack from 10:30 to 6 p.m. At 6 p.m. we had a hard stop and everyone had to present their work. So every team had 5 minutes to present their work and winner was decided based on the voting. So we always encourage people to bring their own project. So this time around we had a project that got resurrected from NANOG 67, PyCon, console servers using Raspberry Pis, and actually they are one of the winners of Hackathon as well, along with NetBuffs. So without any further ado, I'll invite NetBuffs, followed by PyCon, to share their experience of Hackathon and their approach, how they approach solving the Hackathon.
Good afternoon, everyone. I hope you guys are having good NANOG sessions. So we are Team NetBuff. We are students from University of Colorado Boulder. I'd like to thank firstly NANOG for arranging this hackathon and giving us the opportunity to participate in it. I'd also like to thank Oracle and Tesudo for giving us the cloud platform to perform the hack. So the problem statement was given us basically was to network automation. So we needed to build a system to monitor the network and detect the failures. So for moving forward with this, we monitored the paths for all the networks, so all the paths from point A to point B. As you know that a large amount of data is flowing from one point to another, so we use time as a metric to going forward with the monitoring path. Since time complexity we automated the whole script, whole network topology monitoring process, and we made use of some open source tools. So the hackathon goal which we moved forward with was to extract the topology information, like all possible paths, the number of hops, the interface nodes informations. We monitored that and we detected failures for that. If the failures were detected, we raised the necessary actions. So we pass this information from the network topology using BGPLS. BGPLS is a tool that can be used to extract the IGP information and give it to an external entity via BGP. And for that, taking the information out of BGPLS, we use XRBGP. So XRBGP gives us the information in a form of JSON format. And for extracting the information and passing through it, we made use of Python and JSON. And as you can see, we found out the router IDs, router addresses, all that through this information which we got from XRBGP. Then we made, this is the topology which was given to us. We had 6 routers. So we found out the best, all possible paths from point A to point B using a tool, NetworkX. NetworkX is a tool that can graph the network, and you can study structures, dynamics, and functionalities. So this is the workflow we followed. So first we created the probes that we need for monitoring. Then we send a probe from host A to host B. On the same machine, we received the same probes. We extracted the information regarding the time between and the sent and the received packets. We calculated those time, calculated the time difference between them, and set a threshold. If the delay that had was greater than the threshold, we generated a ticket. Otherwise, this whole script was going back to step 1 and continuously monitoring the whole process. So the for probe creations, we made use of Scapy. Scapy is a strong, powerful tool in Python package, which can use to create packets and send from point A to point B. So we created IPGRE packets, different more packets which had source and the destination addresses. We integrated those packets in a single variable, and we integrated the payload which contained the time. Then we send the packet using the Scapy function. And as you can see, this is the screenshot of the packet which we received back on the instance. So we calculated the time difference. For that, we fetched the information from the received packet and took the difference of the send time and the receive time and set a threshold for that. If the value goes beyond the threshold, we automated a script that can generate an email and which can raise the ticket. So this is a small demo of what we did with the tools which I mentioned earlier. So on the right, you can see we created a Python script that sends the packets from host A to host B. And on the left-hand side, it's the Python script that is receiving the packets, fetching the information regarding the time, and displaying an error message. So when this error message takes place, we report a failure and send an email which will raise a ticket. So for raising the ticket, we have used Freshdesk. So as you can see in the highlighted part, the error message contains the error, like what is the error, like high latency, and on which route, like which route the packet is taking. On that packet, we are raising an error. So as you guys know that Hackathon is one-day event, and we did many things, but we still had many things in mind to do. So as this hack was constrained to 6 routers, we thought of scaling. We have something scripts ready, like we can scale this whole hack for a complex network. Also, we can take the failures and reroute the traffic to a different paths, because we already have the path from point A to point B, different paths from point A to point B. Also, we can visualize the error message using a graphical tool and create a dashboard regarding that. For that, we were thinking to use Grafana. So there were many things that we learned from this hack. We learned many tools which were presented us by Oracle. We had a chance to dig into it. Like I said earlier, like time is constraint, time is money. we learned that how network programmability can be used to reduce the time complexity and make an efficient network automated script. Since it was a one-day event, we needed to plan, so we planned step by step, created a workflow, and got the results. Also, we divided the work among our teams according to the strengths, and then we integrated those steps and got the results. So there were many tools which we got, and we didn't know about it, but we were stuck at many points, but we didn't give up and move forward with it. That was the main strength which we think we got from this hack. These are the team members that performed the hackathon together. And thank you guys. I'd like to thank NANOG and Oracle for this event. I'd also like to thank my professor Jose Santos, Kevin Epperson, and Levi Perigo for giving us the opportunity to do this. Thank you.
Hi everyone, I'm Ryan Rodden from Conversant Media. I'm Ryan Rodden, I'm with Conversant Media, and I was working with Anand, Oliver, and Taylor on the PyCon project. All right, so the theme of the NANOG 76 hackathon was active monitoring. As mentioned by Syed, I had brought in a project from NANOG 67, which was to establish console server infrastructure using open source self-assembling or self-discovering framework and commodity hardware. Some common issues that I think we've all experienced with managing console infrastructure, especially across multiple locations, console vendors, and capability of local personnel is the islands that we have of different devices that perform different function or service different devices, poor documentation of what devices are connected to what console, especially when you need it most, little or no proactive testing of what devices are available and working correctly on console, and then the pain that can come with when you need the console, but you can't necessarily find it, you don't know if it's hooked up or if it's working correctly. I think everybody has probably experienced the case where you reach out to an on-site contact, whether it's a non-technical individual in an office, whether it's new or broken, or a remote hands personnel who has to troubleshoot your console and get you, hopefully, your out-of-band access working. So the project born of the 2016 NANOG 67 hackathon was to develop an open source self-discovering framework that would allow you to use commodity hardware operating over a trusted or untrusted network to give you a single view of all your console capabilities, regardless of location and maybe even vendor. Over time, this would then give you the means to pick and implement the advanced features that you want, such as user concurrency, whether it's read or read-write, logging of console output to file or to syslog, and then also point and click access, ideally, such as is offered in some of the more advanced commercial platforms. So in theory, all you need is a USB serial adapter and then some device to give you that remote access. The Raspberry Pi is a platform that I think we're all familiar with the ubiquity of, and there's a lot of other similar ones that can be used to drop and get this capability wherever you need it. The idea is to have a API and a framework where you power up a device and it runs an agent that can self-report things such as its interfaces, its addresses, and the console ports that are available so that you can maintain an inventory of all the console connections available in the different locations that are deployed. Whether the connectivity is 3G or 4G out-of-band or third-party vendor-provided connectivity or a local trusted network, this would give you the means to access those devices over whatever is in the middle. The actual workflow ends up being that you have the periodic registrations from the Raspberry Pis out in the field. They call to the web server and in turn get back some amount of configuration information. That will be used to configure the local console ports, as well as step 3, which is optionally open an SSH tunnel to a server in your central infrastructure. This way, regardless of who else's network is in the middle, what vendors or firewall policy might be in there, as long as you have that SSH capability back to your central location inside or outside your network, you can then port forward or port back to the device in question to access it for console or other troubleshooting purposes. So the Raspberry Pi is inexpensive. You can buy a bunch of them and deploy them and use them for either this purpose or other troubleshooting or probe purposes. This is to some degree how this is on theme with the hackathon, even though it was a project off of the in-band testing and monitoring aspect. The initial work in 2016, we used Python 3 with Flask and Bootstrap and minimal external dependencies to provide a web server and API where the agent would be fired up and given just the endpoint of the API to register with, and then everything else would be pulled from the server side config. This web server would also provide the UI for the listing of devices, console ports, addresses, and status of the infrastructure. The self-registering agent would then also be able to open that SSH connection to an SSH jump box, essentially. So after that hackathon, the next steps were to add some more web and UI capabilities to support the configurability of the environment, establish the actual programmatic console access, the in-browser console access once that foundation was in place, and potentially other things like add a proxy agent for joining other vendors' infrastructure or registering with the API on their behalf, or physical configurations for deploying these in racks or whatever level of ruggedization required for an environment. So the agent starts up. It will self-publish its own hold time based on how volatile it expects to be. Its host name, so it can be uniquely enough identified. Its interfaces and addresses, both IPv4 and IPv6, and then the list of whatever TTYs are available locally that should be able to provide console access. From the server towards the bottom of this screenshot, we then get back the status of the registration and then any other configuration information, for example, the tunnel server and port to register on. The UI provides a fairly straightforward list of the devices. One of the goals that we chose were the top 3 to add some additional capabilities and establish some level of the console access. So in this screenshot, we have the list of devices, in this case, the one main demo device, the 2 ports available on it, and then the descriptions, which is a new capability added throughout the process of learning and working on the project together. In the device details, we added the click to configure capability towards the bottom here to be able to provide, instead of going into configuration files and mapping ports and descriptions on everything, hopefully providing configurability through this single view as well, regardless of how many of the deployed devices or ports there are. That same mechanism hopefully can be used to configure baud rates and other configuration necessary to light up the downstream downstream serial ports and persist that configuration over time. We also were researching the WebSockets capability used to get an in-browser access to the console so that when you have the list of devices and console ports available, you just click on one and you are able to access the console of the downstream device. We got some islands of the connectivity and proof of concept working. In this case, the WebSockets server was up and running and starting to be integrated into the code base by the end of the day, and we were able to carry events from one browser through the server and back, potentially laying the groundwork for being able to talk to a console server backend and provide concurrency between multiple users. So throughout the day, the team and individuals researched a bunch of new topics that were outside of our comfort zone. WebSockets was something new to all of us, especially being network engineers, not doing much GUI development. Interacting with the TTYs themselves via Python, the serial module specifically, interacting with the device directly to eliminate external dependencies. And more features using the Twitter Bootstrap and some old rusty jQuery skills we all dusted off to add the client-side capability for configuration. So with this, we implemented the various UI tweaks and provided some experience for the college student that was on our team. We also integrated that WebSockets proof of concept to be able to interact with the users and push and pull data from the server without having to pull the server with repeated HTTP requests. Our takeaways were that Flask and Bootstrap and other similar technologies in Python 3 and elsewhere provide a simplified means for non-developers like network engineers to mock up or create this kind of infrastructure. However, WebSockets and things like synchronous I/O and then the multi-threading of those two with the web server, talking to the various backend services are substantially more complicated. So we got a great experience to some things outside of our comfort zone, but trying to implement the UI workflow and the end-to-end console access will take quite a bit more planning and research. As always, there are less technical takeaways from the skills, as the colleagues on the NetBuffs team mentioned. The soft skills of working with strangers on new topics, meeting some people for the first time, communicating, digging into things and getting outside of your comfort zone. It is inherently uncomfortable, but it's a fun experience, and it's great to have that time set aside to do it. So there's other future work great options left for this project. One is to continue integrating the WebSockets for console access, basic authentication, so you can have a privileged system of read, write, no access. Identify what the ideal hardware configuration would be for a proof of concept deployment and maybe in one of our employers' networks to see how this holds up to some real world use cases. One of the best, most interesting ones is being able to drop one of these in a box with a bunch of USB dongles and get it to an office somewhere and just have it get cabled up with a data provider's USB dongle or something. Being able to extend and abstract the configuration of the server and agent behavior, as well as to continue to add UI access to the configuration of the downstream device serial ports. And then another interesting idea is if you have a bunch, say you have a bunch of Cisco 2901s deployed with 64 serial ports all over your network in these islands, well, it's kind of like the XKCD comic of when you want to create a new standard, you suddenly just add one more thing to the mix and you haven't really solved anything. For this to add value in an existing console infrastructure, an ideal case might be having a proxy agent that is able to talk to your existing console infrastructure and register it in the UI and then proxy commands back and forth out of that as well. So again, as mentioned by our colleagues on NetBuffs, thank you to Testudo and Oracle and NANOG for organizing this event. It really is great to get out and do something different and set aside this time when during our week and our day jobs it may be hard to go out and do something new like this. If anybody's interested in the code or contributing, I do hope to continue working on this project. It's got some potential promise for this decentralized aspect of monitoring and console infrastructure. There's the GitHub URL, and any contributions are welcome. Thank you. So there are a few minutes left if anybody had any questions about the hackathon or either of these projects. Both teams are available. All right, thank you.